Okay, this is the FSMQ Level 3 Data Analysis Pilot from June 2017, and it makes up part of the AS Use of Maths Pilot A-Level. Our first section is on vehicle registrations. This is going to be a percentages section. There are certain key bits which have a habit of confusing people. One of those is going to be this bit here. So the fact that July to September is quarter 3. The year's split up into 4 quarters, January, February, March being your first quarter, April, May, June the second. Third quarter is the one we're dealing with here from July to September, and the fourth quarter being October, November, December. So this is all referring to your third quarter. We're told certain bits of information about this year and previous years. So we know that in the third quarter of 2015, there are this many vehicles registered, and so what we're going to be asked to do almost certainly is going to be take our 2015 value, and then we'll have to compare it with some of the other ones. So we know that 2014, so we know that between 2014 and 2015 we go up by 8%. So if we take our old value as 100%, our new value is going to be 108% because it's up by 8%. So if we are going in this direction, we would times by 1.08, and if we were going backwards we would divide by it. So if we're looking to find the 2014 value, we have our 2015 value and can divide it by 1.08 in order to get 2014. We've got something very similar here at 2%, where we're talking about the figure in 2002. So if they wanted our 2002 data, we've got 2002, which will be our 100% because it's our older one, and it goes up to 2015, and that was 2% lower. So 2% lower than 100% is going to be 98%. So if we want to get from 2002 to get 2015, we would times it by 0.98. So if we want to go back the other way, we can then divide it. This is something you would have seen at GCSE on percentage multipliers. There are a certain couple of other bits that are of interest within the diagram. So we've got this section here where you have an increasing trend. You've got it increasing here and staying fairly flat in this first section. And then the other bit, we've got decreasing trend for this section and a decreasing trend for this first section. The reason that they're talking about the third quarter is because in 2001 they started a new system of vehicle registrations where new plates were issued in September, so the end of the third quarter, and in March at the end of the first quarter. Prior to this, they were only issued once a year in August. So if we take some of the useful information from this section, this number here is going to be the one that we then have to move into the second half. So this second half is only telling us about the Q3 of 2015. So this Q3 of 2015 was the value that we had in the beginning of this many vehicles. Now this is then split up into two diagrams. You've got the cars represented with 81.3% of all vehicles. So these vehicles here, your 100% is this. So the remaining vehicles, that other section which would have come in this bit, then becomes this donut down here. In previous years, they've done something very similar to this, where they then talk about something that is linked. So here we are told that we have registered cars. So the fact that it's cars is important because this section here is our cars. So we can potentially work out how many cars there were that were registered in or during the third quarter of 2015 by working out 81.3% of the total number of vehicles. And then this links in nicely because what we've got here as the end of September 2015 is actually the end of the third quarter. So given that this is at the end of the third quarter and we know how many are registered during the third quarter of cars, because this is about cars, so this one's about cars, we could potentially from there be asked about the end of the second quarter. So taking these cars off, you could be asked about your percentage increase. So looking at the percentage that was here, work backwards to the end of the second quarter, beginning of the third quarter, because if you're doing percentage increase, you would need the original value. So you've got your change divided by your original. Section B on our datasheet is the UK Snooker Championships 2015. This is where Neil Robertson achieved his maximum break. Now, this one's a bit of an anomaly because a maximum break in snooker is 147. Yet, what the frame in which he achieved that is actually this one that's registered as 151. So we know that he won 10 frames to 5 frames against Liang Wenbo. So looking at this section logically, we know that this first value is going to be Neil Robertson's score, and the second value of each one is going to relate to Liang Wenbo. So we've got 15 of these different things, and they have already very kindly calculated the mean and the standard deviation scored by Neil Robertson. So we've got mean and standard deviation. So sensible things that they're likely to ask us. They are likely to ask us about the mean and the standard deviation that Liang Wenbo got, and then to compare these in context. They may also decide to just use Neil Robertson and then look at something like the semi-finals with his mean and standard deviation and compare between the semi-final and the final. There's a couple of different bits they could do with this. something like box plots for each player, and then compare your median and your interquartile range, but that's slightly less likely. Okay, so looking at section C, we've got predator-prey relationship. There's a couple of interesting bits of information in that it tells us that these numbers, so the pelts that were caught, are proportional to the two populations. So if they're working with or asking us about populations, then any equations that we found for the pelts will still hold valid. These pelts are both being measured in thousands. So if you've ended up with an answer that looks like you've got 0.6 of a lynx, that's not actually a problem, because it will actually be 600 lynxes rather than a bit of an animal. So traditionally, they've only talked to us at the exam about 10 to 15 points on our data set. So they could do a group of 20 years, because any grouping of 20 years would give us 10 data points, and then they can nice and easily take a first bit and then a bit from the second half, or a separate one to be able to compare to. Things that they are likely to ask us. They are likely to ask us to work out a linear regression and a correlation coefficient. So with this data, you end up with a correlation coefficient that is around 9. So our value of R is around 0.9. So you've got strong positive correlation, which means we've got a strong linear relationship between the numbers or the populations of these two animals. Kind of makes sense, given that realistically the lynx are going to be eating the hares. So the more hares you've got, the healthier families and the well-fed families you're going to have of your lynx. So when you then get your first bit, if we look at the section from 1875 up to 1893, we've got a set of 20 years. So if we were to find the linear regression for that, we end up with an equation that looks like y equals 0.382x plus 12.2. So that's assuming that this one is x and this is y. So things that they like to ask us about this is, what does this tell us? So what does the gradient represent in context? So we would be looking at, for each increase of 1,000 hares, our model suggests that the population of lynx would increase by 382. It does also imply that for each individual hare you get 0.382 of a lynx, but that makes a little bit less sense. So if we were comparing two sections, what we would find is the higher value of R, the stronger the linear relationship between these two populations. They may also ask us to plot a section of these or an individual one on a scatter graph, may also ask us to predict things. So if we look here, we've got a highest value at 137 and a smallest value at 9. So if we're making predictions for the number of links where our hairs are anything up to 137, that's going to be inside our data range, so more reliable. If we look at our links, we go up to 80. So anything up to 80 is going to be more reliable for the links. Anything outside is going to be less reliable. This one goes down to 12. So anywhere between 12 and 80 is going to be reliable. Anything either bigger or smaller isn't. This one goes down to 9. So hairs between 9 and 137, you're going to have a reliable prediction. The only bit where you might have an unreliable prediction is if the year they were talking about was significantly outside of the data set we've got here. So if they were asking us, for example, about the number of hairs in 2001, that's quite a jump from the 1903 that is our biggest year, or our closest year to that. And we don't know what would have happened in North America during that time. And we are looking at the weights, or the estimated weights of fetuses from 8 to 40 weeks. So we know that we're working with weight. We don't know whether we're working with ounces or grams. For the moment, purely based on the fact that we tend to use metric, I'm going to use grams. We are also fairly predictably told that it follows a normal distribution. So this is going to be the normal tables section. We are also told that if a child is above the 90th percentile, it's large, and if it's below the 10th percentile, then it's small. So, realistically, a fairly quick search of the internet gave up this information. So it's an approximation of how many weeks the child is, or the fetus is. This is its average weight. So from the point of view of normal tables, this is going to give us our value of mu. And because we've got the 10th and the 90th, it then potentially enables us to work out what our standard deviation is. This one assumes that we are using a Z value of 1.28, but in reality, from an exam point of view, we have no idea what we're going to be looking at. So the bits that we do know, we know that X is going to be our value in context. And context very helpfully has an X in it, which is just there to help you remember, or at least just fairly convenient. So if we look at how we'd write this, we'd have a probability that big X is, now if we were going to have above the 90th percentile, then we can say that is the probability that X is greater than or equal to, that would be our little x, so that would be the weight of the fetus. So for a large baby, that would be at 0.9 because it's 90%. No, I lied. The probability that it's bigger, so for a large baby, is going to be 10% because it wants the top 10%, 90th percentile. So that's going to give us a probability of 0.1. Now, we know that we can't read 0.1 off a table because it's less than a half. So what we do instead is we say that that's 1 minus the probability of x is less than or equal to little x. So that tells us that the probability, and that would still be 0.1, so the probability that that is less than or equal to x is going to be 0.9, which is your 90%, as you would expect. So the reason that we would look at it as less than or equal to be able to find your 90% is just because you can look up 0.9 on the table and you can't look up 0.1. So it's easier to say that the cutoff is at 90% rather than it's the top 10%. So when we're doing a question like this, the other things that we are going to need to know are mu, which is our mean, sigma, which is our standard deviation. So if we know these three things, then we can work out the probability. So our next step is we would need to be able to work out z, and z is our value in context minus the mean divided by the standard deviation. So you'd use these three values to work out z, and then from there you would get the probability, and we'd have a probability, and that's a thing that you can then read off your tables or your calculator. You will need to calculate with this regardless of which of the bits of information that you know. So that would be z is less than or equal to little z, and that's your probability. You are going to be missing some of these bits of information. If you are missing the probability, that's the easiest situation because you can use your value in context, get the mean and standard deviation from the question, put them into that equation, then work out your probability, and that little z will go in there. If, however, you are missing your value in context, but you have your mean and your standard deviation, then you are going to do the inverse. So you'll start with your probability, and that'll give you, if you're doing this on a calculator, to find out